For those of you who were here last lecture, we started discussing the matrix version of the simplex method just to actually uncover what may be going on behind numerical manipulations. Of course, you've seen a single example of a simplex method using numbers, but that doesn't tell the whole story. It gives you, it's just a manipulation of a set of equations while also paying attention to non-negativity. All right, so this is the problem under consideration. Minimization of some objective function Cx subject to standard form constraints. And I'm assuming A is m by n, and rank of A is equal to m. And then we assumed we have a given basis B which is feasible. So given a feasible basis B, we partition the A matrix as well as the vectors X and C into basic and non-basic components. And we may rewrite the original problem. I don't know if I gave a name to it before. Did I give a name to the original problem before? No name? Anyway, let's just call it P. Okay. We may write P in partitioned form relative to basis B in the following way. Minimize CB XB plus Cn Xn. CB refers to the basic portion of the cost vector. Cn refers to the portion of the cost vector consisting of coefficients of non-basic variables. Of course, these are both row vectors. XB and Xn are the column vectors capturing the basic and non-basic variables. Subject to AX equals B partitions into BX plus BXB plus NXN equals B with, of course, all variables restricted to non-negative values. All right, we also introduced the additional variable Z to simply take the value of the objective function. So Z stands for the value of the objective function. So let's put that also, well, you can put that here also. All right, and we did the following. I stated the row 0 form, which is the minimization of Z subject to Z minus CBXB minus CNXN equals 0 with constrained in partitioned form. And as in the example problem, we work with the boxed portion of the constraints where the top constraint is separated out as row 0. So this is your row 0. That's the objective function row. The remaining rows are row 1 through row m. This part. Okay? So that's a set of equations with m equations in the lower part, one equation in the upper part. All right. Even though we work with this system, we don't quite work it in the way it's stated here. We work it out by multiplying the entire lower portion of the box with B inverse. And then we manipulate the top part in a way to justify the operations of the simplex method. So how do we do this? We do it as follows. First of all, let's just state the current basic feasible solution. as defined by the current basis. So the current basic feasible solution is obtained by setting the non-basic variables equal to 0. That's a vector of zeros. And then solve for xb under the assumption xn is equal to 0. So that gives xb equal to, when xn is equal to 0, of course, bxb equals b is a square system, which is solvable. It has a unique solution, which is b inverse b. Okay? And I gave a name to what you see on the right side. We call this the modified version of b, which is b bar. Okay? That's the notation used in your book. So let's just stick to that. And the objective function is also defined by this. Z is equal to cbxb plus cnxn. Xn is 0, so it will be cb times the xb vector, which is b inverse b or b bar. Okay? And because this is a particular solution, let's just mark it as xm bar, xb bar, and z bar. It is the current basic feasible solution. Okay, and I assumed that B is a feasible basis, okay, by assumption, which means that what you obtain here for xb bar is, by assumption, greater than or equal to 0. It's non-negative in each component. I probably did not state that in the previous lecture. Nevertheless, let's just keep that in mind by assumption. Okay? Okay, so let me just continue here. So the set of equations bxb plus nxn shows up in the Tableau in the following way. Everything is pre-multiplied by b inverse, so you have xb, b inverse times b gives you identity, plus b inverse times n multiplying xn. And on the right side, of course, you again have pre-multiplication by b inverse, which is b inverse b, or b bar. Okay? And of course, that tells you that as soon as xn is taken to be 0, xb is equal to b bar. That's what it tells you. The row 0 is taken as follows. We simply take z as cb xb plus cn xn, but we substitute for xb the solution we have here. So this will be cb times xb. xb here, from here, of course, xb is equal to b bar, which is this part, minus b inverse n xn. And so you just substitute that here. And then you've got another cn xn term here. And then you multiply this out. cb b bar is simply your z bar, the current value of the objective function. And the remaining part, if you factor out xn, what do we have here? cb times b inverse n. So minus Cn. And then this part, I gave a name to it. This is just a row vector which multiplies or with which you take the dot product of x. And we gave a name to it. We just called it R sub n, the row vector of reduced costs. Vector of the so-called reduced costs for non-basic variables. Okay? I might have written it out with a plus here and flipped the parenthetical part in the previous lecture, but it's the same thing. So don't get confused by that. All right, so hence we have the system, the original system star expressed in the following equivalent way. What is it? It's this. Z is equal to CBB bar, so it will be Z, you take it to the left side, Rn, so as 0 times xb. There's no xb here. For that reason, it has a vector of zeros in front of it, plus Rn times xn, that's equal to 0. I'm just taking it from here, okay? And the other part, we're taking it from here. And that tells me that we have identity times xb plus the matrix B inverse n times xn equals B bar. That's what we have. This is not 0. What is it? It's Z bar. It's supposed to be Z bar, yes. Because we've got a Z bar there, okay? Yeah. Okay, so this is the equivalent way of writing the equations portion of the constraints. The non-negativity, you don't write it down because you keep it in your mind. In other words, you take care of it on the side all the time. For the current situation, the non-negativity is already taken care of because by assumption, the B bar, which is the solution for the XB portion, is non-negative. So this is by assumption. And xn is already 0, so everything is well taken care of. All right. Double star gives the solution for xb and z for any choice of xn. Okay? Because as soon as you specify xn, you know that xb is equal to b bar minus b inverse n times that specified vector xn. Okay? And as soon as you specify xn, again, you know z is equal to z bar minus Rn xn. So z is equal to z bar minus Rn xn, and xb is equal to b bar minus b inverse n xn. This is what you see in the dictionary form. Z and xb on the left side, everything else on the right side, and that's precisely the information you've got in the dictionary form. relative to a given basis. Okay? All right. And it also tells you that as soon as xn is equal to 0, what the current solution will be. All right. So now our interest is the following. Since this gives the dependence of z and xb on the choice of xn, of course, what we want to investigate is it possible to improve the objective function value from the current value 0, z bar downwards? I'm minimizing, so I want to go down, okay? By making xn deviate from its current value, which is 0, all zeros, okay? And how do we make it deviate? Well, we can only make it deviate in one way. We can allow certain variables in the non-basic part to be positive, right? But since I'm looking for adjacent basic feasible solutions that will beat the current one in the objective value, I'm going to allow only one variable at a time to become positive. The remaining ones will stay as 0. Okay? So, taking this simply tells you that z as a function of xn is the dot product of rn with xn. So you can write that as a summation rj xj, where j is restricted to the set of non-basic indices. I sub n is the set of non-basic indices of the variables. Okay. All right, so this is just that. And that, of course, tells you that the relative change in z as a function of xj, or if you increase, or if you change xj by 1 unit, the change in z is how much? It's minus rj. That's what it is. We're just looking at the partial derivative of z as a function of these xj's. This is, of course, true for every j in the non-basic part. In the basic part, actually, it turns out that all the changes are 0. We're going to get to that later. Okay? For now, we don't need to deal with that. All right, so this is the situation for a minimization problem, which is the one we have under consideration. We look for a non-basic index j for which the objective value gets smaller, which means you want rj to be positive. In that case, it will go down. Okay? So this also tells you that when the current solution is optimal. If there's no such rj, which is positive, the current solution is optimal. Nothing, you cannot get any better by moving from the current extreme point or current basic feasible solution to an adjacent one. Okay? So that's the termination criterion. If rj are less than or equal to 0 for all j in the non-basic part, then optimum, the current solution is, the current basic feasible solution is optimal. For a minimization, okay? This is a minimization. And for a maximization, of course, you want it the other way around. For a maximization problem. I don't know if you can see it, but there's a little writing there that says for maximization. Okay? So let's just assume B is not an optimal basis, which means that the termination criterion is not satisfied. So we're assuming that there is at least one Rj which is positive, again relative to a maximization problem. Suppose we choose one of them. I don't know which index I chose before. Does anybody remember? Did I call it R sub P or R sub K, or what did I call it? Because I can't really remember these things. Once I do it, you know, it changes from time to time. Yes, Sibel, what is it? R sub P, entering variable. Is it P or something else? Huh? Anyway, let's just call it P. It doesn't matter. Suppose we choose xp as an entering variable. Because we know that its reduced cost is positive, okay? And I mentioned this a number of times. Traditionally, people are tempted to choose the most positive one for minimization, but it could be any positive Rj also, okay? So, what does it mean for xp to be an entering variable? Currently, it's a 0 or non-basic variable, and it will be allowed to become positive now, while all remaining non-basic variables are still 0 or non-basic. And that means some basic variable in the current set of basic variables will go out, will become non-basic. That's how we move from the current basic feasible solution to an adjacent one. That we discussed before, okay? So xp will be allowed to become positive while all xj for j in the non-basic set except the index p will stay as non-basic. In other words, they will continue to be 0. Okay? With that, double star or whatever, what was it? Double star and this one. With that, the solution for z and xp will be, as dependent on the entering variable, will be the following. Z will be equal to the current value minus, now that summation, where is it? Rj, xj, this summation will retain all the zeros here except for j equals p. Okay? There will be only one term which will become different from 0. So that will give you Rp xp as dependent on whatever value you assign to xp. The other part, xp, is going to be equal to the current solution minus or plus. It's minus, right? Minus B inverse times only the corresponding column AP. In other words, I'm picking from B inverse n only the column associated with the entering variable. The other ones will not make any, or they will continue to be 0. Okay? Times xp. That's what we have. Of course, this tells you that for each unit increase in XP, you are getting your Z value going down by RP units. That's what we're trying to do, and that's why we happen to pick XP as an entering variable. But what we are interested in right now is this part. We're done with this. We've already argued why we, choose a variable that has a positive reduced cost here. Okay? All right, so this is the part that we have to deal with. So we use this to decide which basic variable to leave. The basic set of indices. All right, how do we do that? We do it in the following way. We just write this in the form of M equations. So the ith one will have the ith basic variable on the left, which I denoted by x sub b sub I. B sub I stands for the ith basic variable. So if I equals 2, for example, the second basic variable could be variable 17, in which case b sub 2 is equal to 17. Okay? That's the indexing convention. All right, so xbi is equal to the current value, bi bar, whatever that constant is, minus b inverse ap. So I'm going to call that yip for the ith one times xp. This is written out for I equals 1 up to m, where the yip are defined by this vector. Yip is the vector v inverse ap. Okay, so we just define it this way. We just rename v inverse ap as the vector yp, and it has all these components in it, y1p, yip, and ymp. It's a vector with m components. Okay? So I'm just picking the ith one because we're looking at the ith equation here. All right, so at this point, we have m such equations. These equations express the values of the basic variables as a function or as dependent on what you assign to xp. And we just concluded that if yip equals 0, then regardless of what new value you assign to xp, xpi will not change, so it will continue to have the old value. Also, if yip is less than 0, a negative number with another negative here will make positive. xp is also positive, so that will make xpi go up from its current value. So it used to be non-negative, it will continue to be non-negative. Okay? So if yip is less than or equal to 0, then the conclusion is xbi is greater than or equal to the current value, which we know is non-negative. Okay? That's the situation. So there's no, need to worry about these. If, on the other hand, yip happens to be positive, then of course xbi as dependent on xp is simply the current value minus a positive number times another positive number. So this will start going downhill from the current value. And so because of that, you want to ensure that it stays non-negative by not making xp too large. Okay? You want to make xp large because each unit increase in xp gives you rj units of reduction in z. But if you make it too large, then this may become negative. That's what you want to prevent. So this must be imposed. And it must be imposed only for such I, for those I for which the multiplier YIP is positive. Accordingly, we pick we compute the minimum ratio of this. Simply tells you that XP must be bounded above by this constant BI divided by YIP. So you look at the ratios of the current values divided by the appropriate coefficients YIP over those I for which YIP is positive. Okay? Of course, if there's no YIP that's positive, you have a different situation. In that case, there's no minimum ratio, which signals for something else, but we'll get to that later. Okay? All right, so this will be realized by some index. So if you look at the set of indices which realize that, you pick one, say index R, and that set of indices which realize the minimum. So R is an index for which BR bar divided by YRP is a minimizer here. Okay? And select XP sub R as a leaving variable. Okay. I think we got to this point, actually. I had to sort of review that because, you know, we can't just start in the middle of everything and expect you to really follow all the arguments. So I hope all the arguments are clear until now. All right, the new solution. So if I define alpha to be the minimum ratio, which is the ratio defined by the rth index, so with this, that's just a positive number, well, non-negative number. Can it be 0? Yeah, of course. If PR happens to be 0, it could be 0. Okay, but the divider here is always positive. Okay. All right. So then, in the new solution, of course, the entering variable XP will be equal to alpha. That's how much you want to increase it, because that's the largest you can make it. Why is that the largest you can make that one? The reason is you want to satisfy this inequality for every such I. So XP is bounded above by every such ratio as long as YIP is positive. Okay? And for that reason, as soon as you exceed or as soon as you assign a value to XP, which is larger than the minimum ratio, you violate at least one of them. Okay? You don't want to violate any of them. So that's why the blocking occurs with the minimum ratio. So, but then rather than making XP smaller than alpha, you want to make it actually alpha, because each unit increase in the value of XP gives you a reduction in Z. Okay, so you want to make it the largest that you are allowed to make it. Okay, so you want to make XP alpha. Let's call that the new solution value. Then how do I define the ith basic variable? Well, it's already defined for you. Where is it? Well, it's defined here, also here. It's the current value of the ith basic variable minus some number here, which is yip, times the value you assign to xp. So the value you assign to xp is, well, let's just call it xp cap. It's alpha. Okay? All right. So that's how you define this. This is for I equals 1 up to m. It applies to each I, regardless of, if the yip is positive or 0 or negative, it doesn't matter. That's how xpi's are dependent on xp cap. Let's separate out the rth1, because rth1 is the exiting one. Okay? So the rth1, let's just write it separately. That's going to be br minus yrp times xp cap, which is whatever, xp cap. And if you rewrite this, let me just rewrite it here. Br bar minus yrp times, xp cap is this alpha, which is br bar over yrp. And of course, this gives 0. That's what you ought to have, of course. That's why you, your rth basic variable leaves. Okay? So, now this variable, which used to be basic, is non-basic now in the new solution. The other ones, they are still basic. The only one that changed role from basic to non-basic is the rth one. All the other ones are still basic. What about this guy? This is a newcomer. It did not used to be a basic one, but now it becomes basic. So now this one is basic. It used to be non-basic. Okay? So that's how you accomplished your swapping of rows. All right, this is how, of course, then we also have a change in z cap. It's the old value minus rp xp cap. Xp cap is a particular value. It's alpha. Okay? All right. So at least I know what the solution is. But then how do we reflect this into all these tabular information, etc.? That's something else. Okay? All right. So the basis matrix, which used to be B, is different now. It's B cap now. Because one of the vectors in B happens to exit, and it's replaced by another one. So if you look at the columns in B, they are going to be the first basic column, the first, these are the columns of the A matrix, etc. Then there's a rth1, which is going to leave. And then you've got the last one. And in B cap, you're going to retain all of the columns. So these are maintained, except the rth1 changes. What is it replaced with? It is replaced with the entering column, which is your A sub P. So this one is different now. All the other ones are the same. That's the newcomer. Okay? So, of course, you can rewrite your problem in the partitioned form relative to B cap if you want to. So if you want to do that, it's going to be minimization of CB cap, XB cap, plus Cn cap. Of course, n will also change. Xn cap subject to B cap, XB cap, plus n cap, Xn cap equals B. But we don't work with this system. We work instead B inverse times the constraints, and the upper side is also modified. Okay, the objective function is also modified. So we work with the system that looks like minimization of Z subject to Z is equal to something. So I'm going to leave that blank for now. Okay. And the lower portion, it's going to be pre-multiplied by B inverse, which will output XB cap relative to the new basis, plus B cap inverse times N cap. N cap is, of course, it's the, again, one column is changed. Xn cap equals B cap inverse times the original B, which is, let's just call it B cap, okay? With non-negativity still imposed. All right, the row 0, I left it blank purposefully. Because what am I supposed to have here? Anybody? I'm supposed to have a 0 vector for the new basic part, plus, actually, was this a minus or a plus? It's supposed to be a whatever. We'll figure that out in a minute. How was it before? Where is it? It's minus on the right side, so it's plus on the left side. So this is supposed to be a plus R B cap, X B cap. That's what you ought to have. What do you think here? Zero or the new Z cap? Where's Z cap? Is it 0 or Z cap? What do you think? It better be Z cap, right? Because when XB cap is 0, you want to have Z equals Z cap. That's what you want to have. Okay? This is what you want to have. Which means that rather than having B cap, XB cap, you want the identity here. Okay? We want the identity for the new set of basic variables. Now, in the old system, we already had the identity, except that it was for a different set of basic variables. Now, the basic set of variables is changed by only one. So, there's only one column of the old B matrix that has changed now. Okay? For that reason, I can create my identity in front of the new set of basic variables quite easily. Quite easily by simply taking the old information on B inverse and actually creating a unit vector for the incoming variable. Okay, so Rn cap, of course, yes. That's Rn cap, yes. And that's also, yeah, I don't know why I made that. I guess I was hurrying through it too quickly. Yeah. All right, this is supposed to be R n cap and X n cap. Okay? All right. I'm going to take a little bit time off from your next recitation hour because I want to finish this up now. Okay? So bear with me for 5 more minutes and it'll be finished. So the old Tableau has the following information. Basic variables, well, you've got 1, 0 here, you've got a vector of zeros here, you've got Rn for Xn, and you have Z bar for that one. This is the old Tableau. You've got the identity for the basic ones, and you've got B inverse N here and B bar here. That's what you've got. Now you want identity for the new set of basic variables, which means that you're going to maintain all columns of the identity except for one column, the column that has changed. Okay? So we now want to create a unit vector in place of the column that entered, which is AP, but its image relative to B is YP. So when you look at the system, this is what you've got. You have the column XP somewhere here. I'm rewriting the old Tableau in the new way. You've got Z here, XP1, XP sub R, which is the leaving variable, and then you've got XP sub M. Okay? These are the variables listed. You've got 1, 0, 0, 0. For X1, depending on if, well, you've got R1 here, the reduced cost for that one, where Rj is defined by CB B inverse A sub j minus C sub j. For non-basic indices, this is the old definition of the Rj. For basic indices, this will output 0. Okay? So whatever R1 is, it could be basic or not basic. It doesn't matter. You've got Y1, 1, YR1, etc., YM1 for the first column. For column P, you've got RP, Y1P, YRP, and YMP. This is for all j, by the way. Okay. And what do we have here? Y1n, YRN, YMN. And then on the right side, we have Z bar, B1 bar, BR bar, BM bar. Okay, that's what we have. We decided that this is the entering column, and we decided that this is the exiting column because the ratios for the positive entries in this column when you inspected the ratios of the current values on the right-hand side column to the positive number in that entering column. The minimizing one happened to be the rth one. Okay? So I'm not going to write down the ratios. So you want to create a unit vector here. Which unit vector? The one that has a 1 in the rth position and zeros elsewhere. So instead of saying a unit vector, we say the unit vector, ER. ER is the unit vector that has a 1 in the rth position, 0 elsewhere. Okay? How do you do that? You divide this. So let me write it here. Pivoting on YRP accomplishes this. And pivoting means you first divide the pivot row, which is your row R. So the new row R is 1 over YRP times the old row R. This is your row R here. Okay? So this is the updating of the pivot row. For I other than R, new row I is going to be, now that you have a 1 here after the division, of course these are all divided by the same number. This one also. Now that you obtain the 1 here, to create a 0 here, what do? You multiply this by y minus y1p and add it to that row. Okay? So for the ith one, you take the old row I, which is already available, and add minus yip times the new row R. In this case, row R is your pivot row. Okay? Which, of course, you can also write down in the following way. Row I minus yip divided by yrp times old row R. Whatever. They're all the same thing. Okay? There's only one other thing that's left, row 0. So no new row 0 is equal to old row 0 plus, in that case, of course, you want to have minus RP. Minus RP. Yes, minus RP times the new row R. Okay? And then if you apply these operations, you will have your appropriate unit vector here, which will also transform the rest of the stuff in the appropriate way. The old unit vectors underneath the old basic variables will be maintained. They will not be affected because they all have zeros, and so they won't be affected. And you got what you want. It was too much, I think, for one day. Huh? All right, let's stop here.